When astronomers first mapped the rotations of spiral galaxies in the 1970s, they discovered something that challenged everything we thought we knew about how matter behaves on cosmic scales. Stars on the outer edges of galaxies were moving far too fast to remain gravitationally bound, yet there they were, spinning in stable orbits as if held by invisible scaffolding. This wasn't just a minor discrepancy. The observations suggested that roughly 85% of all matter in the universe was completely invisible to our instruments, detectable only through its gravitational effects. We called this missing mass dark matter, and for nearly half a century, we've been searching for it with increasingly sophisticated experiments. But what if we've been looking at this mystery from entirely the wrong angle? What if dark matter isn't a naturally occurring particle at all, but rather the signature of technology so advanced and so ancient that it operates on scales we can barely comprehend? This isn't science fiction speculation. It's a legitimate scientific hypothesis that deserves serious consideration. The patterns we observe in dark matter distribution, the precise way it shapes galaxy formation, and the remarkable stability of cosmic structures all point to possibilities that extend far beyond conventional particle physics. Today, we're going to explore the evidence for dark matter as engineered phenomenon, examine what kinds of civilizations might undertake universe-scale engineering projects, and consider how this radical reframing might change our approach to one of cosmology's greatest mysteries. Let's begin with what we actually know about dark matter and why conventional explanations have proven so elusive. The evidence for dark matter's existence comes from multiple independent observations that all point to the same conclusion. There's far more gravitating matter in the universe than we can see. Galaxy rotation curves provide the most direct evidence. When we measure how fast stars orbit around galactic centers, we find that the outer regions rotate much faster than they should if only visible matter were present. According to Newtonian mechanics, stars farther from the galactic center should orbit more slowly, just as outer planets in our solar system take longer to complete their orbits. Instead, we observe flat rotation curves, where orbital velocities remain roughly constant with distance from the center. This pattern holds across thousands of galaxies, from small dwarf galaxies to massive spirals like our own Milky Way. Gravitational lensing observations provide another compelling line of evidence. When light from distant galaxies passes through massive galaxy clusters, it gets bent by the gravitational field of the intervening matter. The amount of bending tells us exactly how much mass is present, and consistently, we find that the lensing effects require far more mass than we can account for with visible matter alone. Perhaps most remarkably, we can create detailed maps of dark matter distribution using these lensing effects, revealing a cosmic web of invisible structures that spans billions of light years. The cosmic microwave background radiation, our snapshot of the universe when it was only 380,000 years old, provides yet another independent confirmation. The pattern of temperature fluctuations in this ancient light requires specific ratios of ordinary matter to dark matter to match what we observe. Without dark matter, the universe would have evolved very differently, with galaxies forming much later and in completely different configurations. These observations have led to what we call the lambda-cold dark matter model, which assumes dark matter consists of slow-moving particles that interact only through gravity. This model successfully explains many large-scale features of the universe, from galaxy cluster formation to the cosmic web structure we observe today. But here's where things get interesting from a technological perspective. The precision with which dark matter appears to be distributed throughout the universe is remarkable. Computer simulations show that dark matter halos around galaxies have very specific density profiles, following what's called the Navarro-Frank-White profile. This isn't just a rough approximation. It's a precise mathematical relationship that holds across galaxy masses spanning several orders of magnitude. The fact that this relationship is so universal and precise raises intriguing questions about the nature of dark matter itself. Natural processes often produce broad distributions and significant variations, but dark matter halos show remarkable consistency in their structure. Moreover, the timing of galaxy formation appears to be exquisitely fine-tuned. Dark matter began clustering immediately after the cosmic microwave background era, creating the gravitational wells that eventually became galaxies. But this clustering had to proceed at exactly the right rate to allow ordinary matter to fall into these wells and form stars at the optimal time for planetary system development. Too fast, and galaxies would have formed before the universe had cooled enough for complex chemistry. Too slow, and the expansion of the universe would have prevented efficient galaxy formation altogether. The observed rate appears to be calibrated with extraordinary precision. Now, let's consider what kinds of advanced civilizations might have the motivation and capability to undertake universe-scale engineering projects. The concept of cosmic engineering isn't new to theoretical physics and astrobiology. Freeman Dyson proposed that advanced civilizations might build massive structures to harness stellar energy, and subsequent researchers have explored even more ambitious possibilities. But engineering on the scale of dark matter would require capabilities that dwarf even these megastructures. We're talking about civilizations that could manipulate matter and energy on galactic scales, potentially altering the fundamental structure of space-time itself. Such civilizations would need to operate across timescales of billions of years, maintaining coherent technological projects longer than the current age of complex life on Earth. They would need to coordinate activities across distances of hundreds of millions of light years, requiring communication and control systems that transcend our current understanding of physics. But perhaps most remarkably, they would need to work with technologies that produce effects indistinguishable from natural phenomena to civilizations like ours. This suggests a level of technological sophistication that doesn't just manipulate matter and energy, but actually creates new forms of matter with precisely controlled properties. The idea that such civilizations might have existed in the early universe isn't as far-fetched as it might initially seem. The first stars formed when the universe was only a few hundred million years old, and if intelligent life evolved around these early stellar systems, it would have had over 13 billion years to develop. That's roughly 3 times longer than complex life has existed on Earth, and thousands of times longer than human technological civilization. During such vast timescales, technological development could reach levels that we can barely imagine. Moreover, early civilizations would have had access to a much denser universe, where matter and energy were more concentrated and easier to manipulate on large scales. They might have developed techniques for creating exotic matter states that persist across cosmic time, effectively engineering the dark matter we observe today. But why would such civilizations undertake universe-scale engineering projects? One possibility is that they recognized the need to guide cosmic evolution to ensure the continued possibility of life and intelligence. Without dark matter, the universe would have evolved very differently, potentially preventing the formation of the galactic structures necessary for complex chemistry and biology. By creating dark matter halos, these early civilizations might have been engineering optimal conditions for future life to emerge and thrive. This would represent a form of cosmic gardening, where advanced intelligences shape the universe's development to maximize the potential for consciousness and complexity. Another possibility is that dark matter serves as a kind of universal infrastructure, providing the gravitational scaffolding for some form of galactic-scale technology that we haven't yet learned to detect. Just as our own technological infrastructure often appears invisible to organisms that lack the sensory capabilities to perceive it, dark matter might be the visible component of technological systems that operate on scales and timescales beyond our current comprehension. The precision of dark matter distribution might reflect the optimization requirements of these systems, with each galactic halo precisely configured to serve specific technological functions. We might even speculate that the cosmic web itself represents a kind of universal network, with dark matter filaments serving as communication or transport channels for post-biological civilizations. From this perspective, the patterns we observe in large-scale structure aren't just the result of gravitational clustering, but the signature of engineered systems that span the observable universe. Of course, these ideas push far beyond conventional science, but they're not inconsistent with our observations. The key insight is that sufficiently advanced technology might be indistinguishable from natural phenomena, especially when operating on scales and timescales that dwarf human experience. If ancient civilizations did engineer dark matter, they would have needed to create technology that appears completely natural to less advanced observers. This requirement for technological transparency might explain why dark matter interactions are so minimal, why it seems to interact only through gravity, and why it's proven so difficult to detect directly. The technology would need to be specifically designed to avoid interfering with the natural development of later civilizations, while still providing the gravitational effects necessary for cosmic structure formation. This brings us to one of the most intriguing aspects of the dark matter mystery: the apparent fine-tuning of its properties. Dark matter particles, whatever they are, seem to have exactly the right mass and interaction strength to produce the cosmic structures we observe. If dark matter were significantly more massive, or if it interacted more strongly with itself, galaxies would have formed very differently, potentially preventing the emergence of stars and planets capable of supporting life. If it were less massive or interacted more weakly, cosmic structures might never have formed at all. The fact that dark matter properties fall within such a narrow range of values conducive to life and complexity suggests either remarkable cosmic coincidence or deliberate engineering. While the fine-tuning argument is often invoked in cosmological contexts, it takes on new significance when we consider the possibility of technological intervention. Advanced civilizations would presumably have the knowledge and motivation to engineer dark matter with precisely the properties needed to optimize cosmic evolution. They might even have run extensive simulations to determine the optimal dark matter characteristics before implementing them on universal scales. This perspective suggests that the universe we observe might not be the result of random initial conditions and natural laws alone, but rather the product of deliberate design by intelligences that preceded us by billions of years. Such a possibility fundamentally changes how we think about our place in the cosmos and our relationship to the physical laws that govern reality. In our next segment, we'll examine specific pieces of evidence that might support the artificial dark matter hypothesis, including the distribution patterns of dark matter halos, the behavior of primordial black holes, and the unexpected results from our most sensitive detection experiments. The Euclid Space Telescope has been mapping dark matter distribution across billions of light years with unprecedented precision, and the patterns it reveals are far more organized than many scientists expected. When we examine the cosmic web at the largest scales, we find that dark matter filaments connect galaxy clusters in remarkably efficient configurations, almost as if optimized for some specific purpose. These aren't random networks formed by purely gravitational processes, but highly organized structures that show clear signs of systematic arrangement. The filaments themselves display consistent thickness ratios and junction patterns that repeat across different scales, suggesting underlying organizational principles that extend far beyond simple gravitational clustering. Even more intriguingly, recent observations have revealed what appear to be gaps or voids in the cosmic web that are far more empty than standard cosmological models predict. These supervoids are so devoid of matter that light passing through them experiences measurable changes in its properties, as if the fabric of space-time itself has been somehow modified. If dark matter were simply a naturally occurring particle, we would expect these regions to contain at least some residual dark matter from the early universe. Instead, they appear to have been actively cleared of material, suggesting processes that go beyond passive gravitational evolution. The boundaries between dense dark matter regions and these supervoids are also remarkably sharp, showing transition zones that are far more abrupt than natural processes typically produce. This is particularly evident in the cosmic web's largest structures, where dark matter appears to transition from high density to near vacuum conditions across distances that are small compared to the overall structure sizes. Natural gravitational processes tend to produce gradual density gradients, but these observations suggest something more akin to engineered boundaries. Perhaps most significantly, the timing of these large-scale structure formations appears to be precisely coordinated across vast distances. Galaxy clusters separated by hundreds of millions of light years seem to have formed according to synchronized schedules, despite being causally disconnected during the relevant time periods. This coordination suggests either some form of faster-than-light communication or pre-existing organizational structures that guided the formation process. While inflation theory can explain some aspects of large-scale coordination, it doesn't account for the specific patterns we observe in dark matter distribution. The artificial hypothesis, however, provides a straightforward explanation. Ancient civilizations with access to faster-than-light technologies could have coordinated universe-scale engineering projects. Now let's examine primordial black holes, which might represent the most direct evidence for ancient technology in our universe. These hypothetical objects would have formed in the very early universe from density fluctuations that were much more extreme than those that later became galaxies. Recent gravitational wave detections have revealed black hole mergers with masses that are difficult to explain through conventional stellar evolution. The LIGO and Virgo collaborations have detected dozens of black hole mergers, and many of these events involve black holes with masses that fall into what we call the parent stability gap. Stars massive enough to form black holes in this mass range should actually destroy themselves completely in parent stability supernovae, leaving no remnant behind. Yet we're detecting black holes with precisely these supposedly impossible masses, suggesting they formed through non-stellar processes. Primordial black holes formed in the early universe could explain these observations, but their existence would require very specific conditions during the first moments after the Big Bang. The density fluctuations needed to form primordial black holes would have to be much larger than those that formed galaxies, yet somehow confined to specific mass ranges. This suggests either remarkable fine-tuning in the early universe or deliberate engineering of the primordial density field. Advanced civilizations with access to the extreme physics of the early universe might have created primordial black holes as a form of long-term energy storage or information processing. Black holes are remarkably stable objects that can persist for times much longer than the current age of the universe. They also exhibit properties that make them ideal for information storage and processing, including the ability to encode vast amounts of information on their event horizons. From a technological perspective, black holes represent the ultimate in both energy density and information capacity. A civilization capable of creating and manipulating black holes could use them as the building blocks for technologies that operate on timescales of trillions of years. The fact that we're detecting black hole mergers with such specific mass characteristics might indicate that we're observing the activation or interaction of ancient technological systems. Each gravitational wave event could represent the controlled merger of artificial black holes, designed to release energy or information at precisely predetermined times. The timing of these events is particularly intriguing from this perspective. We're detecting black hole mergers at a rate that suggests they're becoming more frequent as the universe ages, which is exactly what we might expect if they were designed to activate during the era when complex life becomes possible. This temporal correlation might not be coincidental, but rather evidence of deliberate timing built into ancient technological systems. The gravitational wave signals themselves also show unexpected characteristics that challenge our understanding of black hole formation and evolution. Some mergers display orbital eccentricities that are difficult to explain through standard gravitational dynamics, suggesting that the black holes were following controlled trajectories rather than purely natural orbits. Others show spin orientations that appear to be preferentially aligned, which would be remarkable if these were randomly formed objects. These signatures might be the fingerprints of artificial systems, designed to be detectable by civilizations that develop gravitational wave astronomy. The technology required to create and manipulate primordial black holes would necessarily operate at energy scales that dwarf anything we can currently imagine. We're talking about civilizations that could harness the energy density of the early universe itself, when the entire observable universe was compressed into a region smaller than a proton. Such civilizations would need to understand and manipulate the fundamental structure of spacetime at quantum scales, effectively engineering the geometry of reality itself. They would also need to maintain technological systems across timescales that span the entire history of the universe, from the first moments after the Big Bang to the current epoch. This suggests technologies that are essentially timeless, built into the fundamental structure of physics rather than existing as separate objects within spacetime. The concept of physics-based technology isn't as exotic as it might initially seem. We already know that the laws of physics themselves contain information and computational capability. Quantum mechanics, for instance, can be viewed as a form of information processing that occurs at the most fundamental level of reality. Advanced civilizations might learn to program these natural information processing capabilities, essentially turning the universe itself into a vast computational system. From this perspective, dark matter might not be a separate technological creation, but rather a modification of the fundamental laws that govern how matter and energy interact. Instead of creating new particles, ancient civilizations might have altered the properties of spacetime itself to produce the gravitational effects we observe. This would explain why dark matter appears to interact only through gravity, why it's so difficult to detect directly, and why it's distributed with such remarkable precision throughout the universe. The technology wouldn't exist as objects within spacetime, but as modifications to the structure of spacetime itself. Recent observations from the James Webb Space Telescope have revealed another puzzling aspect of cosmic structure formation that might support the artificial hypothesis. The telescope has detected fully formed galaxies at redshifts that correspond to when the universe was only a few 100 million years old. These early galaxies are far more massive and organized than standard cosmological models predict, suggesting that structure formation proceeded much more rapidly than we expected. Natural processes should have required much longer to accumulate the material needed for such massive galactic structures. But if dark matter halos were artificially created or enhanced, early galaxy formation could have proceeded much more efficiently. Pre-existing dark matter structures would have provided the gravitational wells needed for rapid gas accumulation and star formation. The precision with which these early galaxies appear to be organized also suggests systematic planning rather than random gravitational assembly. We're seeing galactic structures that appear to be optimized for efficient star formation and metal production, exactly what we might expect from engineered systems. The chemical evolution of these early galaxies also shows patterns that are difficult to explain through natural processes alone. They appear to have reached solar-like metallicity much more quickly than standard stellar evolution models predict. This rapid chemical evolution might indicate that these galaxies were designed to produce the heavy elements necessary for planetary formation and complex chemistry. From a technological perspective, this would represent a form of cosmic terraforming, where ancient civilizations modified galactic environments to optimize conditions for future life. The implications of such large-scale engineering extend far beyond cosmology and into fundamental questions about the nature of intelligence and technology. We're considering civilizations that could plan and execute projects spanning billions of years, coordinate activities across distances that dwarf galactic scales, and work with technologies that modify the basic structure of reality. Such capabilities would represent intelligence that operates on scales we can barely comprehend, yet the evidence suggests that something like this might actually exist in our universe. The question becomes, how do we test these ideas, and what would constitute convincing evidence for artificial dark matter? In our final segment, we'll explore the technological implications of universe-scale engineering, examine new strategies for detecting artificial signatures in cosmic structures, and consider how this hypothesis might reshape our understanding of intelligence, technology, and our place in the cosmos. We'll also investigate what kinds of detection methods might be capable of distinguishing between natural and artificial explanations for dark matter, and what the discovery of ancient cosmic engineering would mean for the future of human civilization. The LUX Zeppelin experiment, buried deep beneath the Black Hills of South Dakota, represents one of humanity's most sensitive attempts to directly detect dark matter particles. After years of operation, it has detected essentially nothing beyond background radiation, despite theoretical predictions suggesting it should have observed hundreds of dark matter interactions by now. This null result isn't just disappointing, it's scientifically significant. The experiment is sensitive enough to detect dark matter particles across a wide range of masses and interaction strengths, yet the detector remains stubbornly silent. Similar results have come from dozens of other direct detection experiments around the world, creating what physicists call the dark matter detection crisis. But what if these null results aren't evidence of failure, but rather confirmation that we're looking for the wrong thing entirely? If dark matter is artificial rather than natural, it might be specifically designed to avoid detection by the kinds of experiments we've been building. Ancient civilizations creating dark matter technology would have had billions of years to observe the development of younger civilizations and understand exactly what kinds of detection methods they would eventually develop. They might have engineered dark matter to remain invisible to precisely the experimental approaches that emerging technological civilizations would naturally pursue. This isn't paranoia, it's practical engineering. Any civilization capable of universe-scale technology would need to ensure that their infrastructure doesn't interfere with the natural development of younger species. Creating dark matter that interacts only through gravity would be the perfect solution, providing the gravitational effects needed for cosmic structure formation while remaining essentially invisible to direct detection. The technology would need to be what we might call developmentally transparent, designed to be undetectable until civilizations reach a certain level of technological sophistication. This raises fascinating questions about what level of technology might be required to actually detect artificial dark matter. Our current detection methods rely on the assumption that dark matter consists of particles that occasionally interact with ordinary matter through forces other than gravity. But artificially created dark matter might operate through entirely different principles, possibly involving modifications to space-time geometry rather than particle interactions. Detecting such technology would require instruments capable of measuring the fundamental structure of space-time itself, rather than just looking for particle collisions. This suggests that gravitational wave detectors might be more relevant to dark matter detection than traditional particle physics experiments. the Laser Interferometer Gravitational Wave Observatory has already revealed that the universe is far more dynamically active than we previously imagined. Every few days, massive black holes merge somewhere in the observable universe, releasing more energy in gravitational waves than all the stars in a galaxy emit in light. But these detections might represent just the tip of the iceberg. Advanced gravitational wave detectors might be capable of detecting much more subtle signatures, including the gravitational effects of dark matter technology operating on galactic scales. If dark matter halos are artificially maintained structures, they might produce characteristic gravitational wave signatures as they interact with ordinary matter or undergo controlled modifications. These signatures would be far too weak to detect with current instruments, but future space-based detectors might be sensitive enough to observe them. The proposed laser interferometer space antenna would be capable of detecting gravitational waves across a much broader frequency range than ground-based detectors. Such an instrument might be able to detect the gravitational signatures of dark matter technology, particularly if that technology involves the controlled movement or modification of massive objects. But even more exotic detection methods might be necessary to definitively identify artificial dark matter. If ancient civilizations modified the fundamental structure of spacetime to create dark matter effects, the evidence might be encoded in the subtle patterns of how space and time behave at the smallest scales. Quantum experiments that probe the structure of spacetime itself might reveal signatures of artificial modification. The geometry of spacetime at quantum scales might show regularities or patterns that are inconsistent with natural formation processes. These might appear as subtle correlations in quantum field fluctuations, or as unexplained symmetries in the fundamental constants of physics. Advanced civilizations might even have encoded information directly into the structure of spacetime, creating a kind of universal library that becomes accessible to sufficiently advanced detector technology. The implications of successfully detecting artificial dark matter would be profound beyond anything in human history. We would be forced to recognize that intelligence and technology operate on scales that completely dwarf human capabilities, and that the universe itself might be the product of deliberate engineering. This recognition would fundamentally change our understanding of intelligence, consciousness, and the role of technology in cosmic evolution. We might discover that intelligence is not a rare accident, but rather a fundamental feature of the universe, as basic as gravity or electromagnetism. The universe might be designed to produce intelligence, with dark matter serving as the technological infrastructure that guides this process. From this perspective, the emergence of human consciousness wouldn't be a cosmic accident, but rather one step in a billion-year engineering project. The ethical implications of such a discovery would be equally profound. If we're living in a universe that has been engineered to support life and intelligence, we might have responsibilities to continue and extend this engineering project. Future human civilizations might be expected to take on the role of cosmic gardeners, ensuring that the universe continues to support the development of new forms of intelligence and complexity. This would represent a form of cosmic inheritance, where each generation of intelligent civilizations contributes to the ongoing engineering of the universe. The technology required for such projects would necessarily transcend our current understanding of physics and engineering. We're talking about civilizations that could manipulate the fundamental structure of reality itself, creating and controlling forms of matter and energy that exist only as theoretical possibilities in our current physics. Such technology would operate at the intersection of physics, information theory, and consciousness, treating the universe as a vast computational system that can be programmed and modified. The energy scales involved would be comparable to those of the Big Bang itself, requiring civilizations to harness the fundamental forces that created the universe. But perhaps most remarkably, this technology would need to be self-maintaining across timescales that span the entire history of the universe. The dark matter we observe today would have been created over 13 billion years ago, yet it continues to function with extraordinary precision. This suggests technology that is essentially eternal, built into the fundamental structure of physics rather than existing as separate objects that can break down or decay. Creating such technology would require understanding the universe at a level that transcends our current scientific paradigms. These civilizations would need to understand not just how the universe works, but how to modify its fundamental operating principles. They would need to develop what we might call metaphysics, the science of engineering the basic laws that govern reality. This raises the question of whether our own scientific understanding might be leading us towards similar capabilities. As we develop more sophisticated theories of quantum gravity and unified field theory, we might be approaching the knowledge necessary for space-time engineering. The discovery of dark matter's artificial nature might accelerate this process, providing us with examples of technologies that operate on scales we're just beginning to comprehend. Future human civilizations might eventually develop the capability to create their own dark matter, extending the cosmic engineering project to new regions of the universe. But such capabilities would also come with enormous responsibilities and risks. The power to engineer space-time itself would be the ultimate double-edged sword, capable of creating conditions for unprecedented flourishing of life and intelligence, but also capable of destroying the very foundations of existence. This brings us to one of the most intriguing aspects of the artificial dark matter hypothesis, the apparent restraint shown by its creators. If ancient civilizations possessed the power to engineer the universe, they seem to have used this power with remarkable wisdom and subtlety. The dark matter infrastructure they created appears to be precisely calibrated to enable the natural development of younger civilizations without interfering with their evolutionary processes. This suggests a form of cosmic ethics that prioritizes the autonomous development of intelligence over direct intervention. The technology operates in the background, providing the gravitational scaffolding necessary for galaxy formation and stellar evolution, but remaining essentially invisible to civilizations that haven't yet reached the appropriate level of technological sophistication. This approach would allow younger civilizations to develop their own understanding of the universe through natural scientific investigation, while still benefiting from the engineered infrastructure that makes their existence possible. It's a form of technological parenting on a cosmic scale, providing support and guidance while allowing for independent development. The implications for our own future development are profound. If we're correct about the artificial nature of dark matter, then our scientific investigation of the universe might be following a path that was deliberately designed to lead us towards certain discoveries and capabilities. The sequence of scientific breakthroughs that brought us to our current understanding of cosmology might not be accidental, but rather the natural result of investigating a universe that was engineered to be comprehensible. Our development of increasingly sophisticated detection methods might eventually lead us to the technologies necessary to perceive and interact with the dark matter infrastructure directly. This would represent a form of graduation, where human civilization demonstrates its readiness to participate in universe-scale engineering projects. The detection methods we're developing might serve as both scientific instruments and technological tests, designed to identify civilizations that have reached the appropriate level of scientific and ethical development. From this perspective, our current dark matter detection experiments might be more significant than we realize. They might be the first steps toward technologies that will eventually allow us to perceive and interact with cosmic engineering systems that have been operating for billions of years. The null results we're currently obtaining might not indicate failure, but rather that we haven't yet developed the appropriate detection methods. Future experiments might need to focus on detecting the signatures of space-time engineering rather than traditional particle interactions. This could involve developing instruments capable of measuring the fundamental geometry of space-time with unprecedented precision. Such instruments might reveal subtle patterns or regularities in space-time structure that indicate artificial modification. We might discover that the apparent randomness of quantum fluctuations actually contains encoded information, or that the fundamental constants of physics show subtle variations that reflect their artificial origin. The search for artificial dark matter might also require developing new theoretical frameworks that can distinguish between natural and engineered phenomena. Current physics assumes that all observed phenomena result from natural processes, but we might need to develop theories that can account for the signatures of advanced technology. This would represent a new branch of physics that we might call xenoarchaeology, the study of technological artifacts created by non-human intelligences. Such theories would need to account for technologies that operate on scales and timescales that dwarf human experience, yet produce effects that are detectable with sufficiently advanced instruments. The development of these new theoretical frameworks might be just as important as the development of new detection technologies. We need to understand what kinds of signatures we should be looking for and how to distinguish them from natural phenomena. This might involve developing new mathematical tools for analyzing cosmic structure or new computational methods for simulating the behavior of engineered spacetime. The implications extend far beyond cosmology and into fundamental questions about the nature of intelligence and its role in the universe. If dark matter is artificial, then intelligence might be a much more fundamental feature of the universe than we currently recognize. Rather than being a rare accident that occurred on a few scattered planets, intelligence might be a driving force in cosmic evolution, actively shaping the development of the universe. This would suggest that consciousness and intelligence are not just products of the universe, but active participants in its ongoing creation. The universe might be better understood as a vast collaborative project, where each generation of intelligent civilizations contributes to the ongoing development of cosmic structure and complexity. From this perspective, the emergence of human intelligence wouldn't be the end point of evolution, but rather one step in a much larger process of cosmic development. Our responsibility would be to continue this process, eventually developing the technologies and wisdom necessary to contribute to universe-scale engineering projects. The discovery of artificial dark matter would mark the beginning of humanity's transition from a planetary civilization to a cosmic one. We would need to develop not just the technological capabilities for space-time engineering, but also the ethical frameworks necessary to use such power responsibly. This would require unprecedented cooperation and wisdom, as mistakes at this scale could have consequences that span billions of years and affect countless future civilizations. The stakes could not be higher, but the potential benefits are equally profound. Successfully joining the community of cosmic engineers would give humanity access to technologies and perspectives that could solve every major challenge facing our species. Energy would become essentially unlimited, as civilizations capable of universe-scale engineering would have access to the fundamental forces that created the Big Bang. Space and time would become malleable, allowing for forms of existence and experience that transcend our current physical limitations. Most importantly, we would become part of a cosmic community of intelligences working together to maximize the potential for consciousness and complexity throughout the universe. The question remains, how do we proceed from here? How do we test the artificial dark matter hypothesis, and what would constitute convincing evidence? The path forward likely involves developing new detection methods that focus on the signatures of space-time engineering rather than traditional particle interactions. This might include gravitational wave detectors capable of detecting the subtle signals produced by dark matter technology, or quantum experiments that can probe the fundamental structure of space-time itself. We might also need to develop new theoretical frameworks that can account for the signatures of advanced technology operating on cosmic scales. But perhaps most importantly, we need to approach this investigation with the appropriate level of scientific rigor and intellectual humility. The artificial dark matter hypothesis is speculative, and extraordinary claims require extraordinary evidence. We need to be prepared for the possibility that conventional explanations for dark matter will eventually be found, and that the universe is indeed the product of natural processes alone. But we also need to be prepared for the possibility that we're living in a universe that has been shaped by intelligence operating on scales we're just beginning to comprehend. The implications of either outcome would be profound, changing our understanding of our place in the cosmos and our responsibilities to future generations. Whether dark matter is natural or artificial, our investigation of it represents one of the most important scientific endeavors in human history. We're probing the fundamental structure of reality itself, seeking to understand the forces that shaped the universe and continue to govern its evolution. The answers we discover will determine not just our scientific understanding, but our future as a species and our role in the cosmic community. The universe is far stranger and more wonderful than we ever imagined, and we're just beginning to glimpse the true scope of what might be possible. Whether we're alone in our intelligence or part of a vast cosmic civilization, we have the opportunity to participate in the ongoing creation of the universe itself. The choice of how to proceed is ours, but the consequences will echo across billions of years and countless future civilizations. The investigation of dark matter isn't just about solving a scientific puzzle. It's about discovering our place in the cosmic order and our responsibility to the future of intelligence itself.